Hi everyone, welcome back. In this video, we're going to discuss intermolecular forces. So as the name suggests, we're talking about forces that exist between molecules, between two molecules, okay? So if my one fist is a molecule and my other fist is another molecule, what we're talking about is what sort of forces exist between these two molecules when they are in proximity with each other or when they are together, okay? And by the end of this video, you should be able to answer questions like, why does water have a high boiling point? Boiling point of water is about 100 degrees Celsius, okay? Why does it have such a high boiling point? Or other things like, why is the boiling point of ethanol, which is this molecule here, okay, why is the boiling point of ethanol higher than dimethyl ether or methoxymethane? Okay, so this molecule here is dimethyl ether. It's also called methoxymethane. Now I've got some numbers here. So as you notice, ethanol has a boiling point of 78 degrees Celsius, whereas methoxymethane or dimethyl ether has a boiling point of -23 degrees Celsius, which means at room temperature, this is a gas, this is a liquid, okay? And so how are these related? Again, if you wonder, they have the same molecular formula, but they have different structures or connectivity. That means these are constitutional isomers of each other. So two molecules which are comprised or composed of the same atoms, the same number of atoms, the same type, everything, they have very different boiling points. Okay, why is that? Or something more fundamental, why doesn't oil dissolve in water? Okay, why does oil not mix with water? Why are they immiscible? So very fundamental questions like these, their answers lie in intermolecular forces. So what we're going to do is, to start off, we're going to learn about the three types of intermolecular forces that exist between organic compounds. And additionally, I'm going to rank them. I'll tell you which force is the strongest, which is the weakest. Okay, so we'll sort of come up with a ranking scheme so that then we can use that ranking scheme to predict which molecules would have a stronger intermolecular force between them. Okay, so we're going to start simple, or with simple in the sense the intermolecular force that's the simplest to understand based on what we've done so far. Okay, and this first force that we're going to talk about is a dipole interaction. Okay, dipole interaction. As the name suggests, we are talking about interaction between two dipoles. Okay, and we've already talked about dipoles, and when we mention here dipoles, we are talking about molecular dipoles. We're not talking about bond dipoles. So if you haven't watched the video on molecular dipoles yet, please go ahead, watch that video before you start with this video. So we're talking about molecular dipoles here, not bond dipoles. Okay, so as an example, let me pick this set of molecules, the one that's given in the textbook also. So you have two molecules that I'm going to draw. Okay, one is isobutylene. It's the name. You don't have to know the name of these compounds, okay? This is isobutylene, and this other molecule is acetone. Isobutylene has a boiling point of -7 degrees Celsius. Acetone's boiling point is 56 degrees Celsius. Okay, so as you can notice, there's about a 60-degree difference in their boiling points. Okay, this is about 60 degrees higher boiling. And if you notice, the only difference between these two molecules, okay, that's another point before we jump into all of this. We can only compare, or I guess it is fair to compare structurally similar molecules. We cannot compare structurally very different molecules and then try to argue or rationalize why one's higher boiling than the other, you know, because then we're going to start running into issues, and we'll talk about some of that later. But we're comparing structurally very similar molecules, because if you look at it, the only difference between these two molecules is a CH2 group here. This may be a good point to like review your bond line structure to Lewis structure. So the CH2 group here compared to an oxygen over there. So what does that change about these molecules that their boiling points are so different? So right off the bat, if you think about it, between these two structures, something that I can notice is that this molecule here, acetone, this has an oxygen atom that's connected to a carbon atom. Now this oxygen here also has lone pairs on it. Okay, it has 2 lone pairs on it. So there must be a bond dipole here. Carbon is less electronegative than oxygen, so I have the positive end here, negative end towards the oxygen. Similarly, the lone pairs, I can draw dipoles for the 2 lone pairs. Since I have 2 lone pairs, going back to the molecular dipole video, to the video there, now we can actually draw a composite dipole here. Okay, we can draw a composite dipole for the 2 lone pairs, and now when we look at it, that composite dipole is pointing up. The dipole for this carbon-oxygen bond is also pointing up. That means overall we have a molecular dipole here which is pointing up. That's our molecular dipole. Okay, so there is a molecular dipole to that molecule. Whereas for this molecule here, that's a carbon, this is a carbon, this is a carbon, these are carbons. Everything is a carbon or a hydrogen, which means this should not have any bond dipole. And if it does not have a bond dipole, it should not have any molecular dipole also. Okay, so we're going to say that the dipole moment for this is basically 0. There's 0 dipole moment, whereas this one has a dipole in it. There is a permanent dipole in that molecule. So now the question is, so if that is true, if this acetone molecule has a permanent dipole in it, and I'm going to just draw the acetone molecule like that, and since the molecular dipole is pointing up, I'm going to say that there is a dipole like that. Okay, so when you have one acetone molecule, this carbon is positive, partial positive, the oxygen is partial negative. And if you have another acetone molecule, okay, if you have another acetone molecule, how would that other acetone molecule orient itself if it is next to this acetone molecule? I would think that, so there are 2 options actually, okay? Let's draw the other option. So if we have another acetone like this right next to it, this also has a del positive here and a del negative here. What I would notice is that in this situation, we have partial positive, partial positive, partial negative next to each other. What do like charges do to each other? Okay, going back to basic chemistry or physics, you know that like repels, right? Like poles repel. So this positive is going to repel that positive. This negative is also going to repel that negative. That means this acetone molecule is going to feel repulsion. Both of them are going to feel repulsion, but they don't have to be oriented like that. If one of the acetone molecules is oriented like this in space with the dipole pointing up, the other acetone molecule will orient in the opposite direction. So you'll have del minus here and del plus over there, partial positive over there. Okay, so that the overall dipole is now like that, pointing down. And so now what happens is we have a partial positive on one end, partial negative on the other end. So these are going to have some sort of a attraction. They are unlike poles or unlike charges. So they're going to attract. And the same is true over here. There's going to be an attraction. And how would the next acetone molecule align itself? It's going to come and align itself like this. So there will be del positive and there's going to be a del negative. So that this del negative can attract that del positive and the del positive can be attracted to that del negative. So basically we develop a network of acetone molecules where they align themselves such that the opposite charges are next to each other and then they attract each other. So this force of attraction, whatever I'm representing by these dotted or dashed lines, that force is going to hold the molecules together. Okay, the two molecules are going to feel a force of attraction between them because of that force. So this force is the intermolecular force because it's a force between two molecules, and this force is called a dipole interaction. Okay, so that's the dipole-dipole interaction. So a dipole-dipole interaction, we can define it as the intermolecular force between two molecules which have permanent dipoles in them. So I think that's the criteria here. The molecules must have a dipole in them. Okay, so this dipole-dipole interaction, we're going to call it IMF just for quick reference. So this is the intermolecular force, and this is going to be there between any molecules which have dipoles in them. Now the same would not apply to this molecule because there is no dipole in it. That means two molecules of isobutylene, if this is one molecule of isobutylene, this is another molecule of isobutylene, when they come together, there is no force, or at least no dipole-dipole interaction between them. There is another force between them, which we're going to see later. Okay, so we can use dipole-dipole interactions to understand why, let's say, acetone has a higher boiling point than isobutylene. Okay, that's the first intermolecular force. Let's look at the second one. The second intermolecular force that we're going to look at is called a London-Dispersion force. You're going to abbreviate LDF. In the textbook, this is referred to as a fleeting dipole interaction. Okay, this is called a fleeting dipole interaction. So let's talk about what a London dispersion force or a fleeting dipole interaction is. So this is applicable in molecules that do not have a permanent dipole. Okay, so this is for molecules that do not have a permanent dipole. So an example or a set of examples here could be butane, okay, 1, 2, 3, 4 carbon molecule. This is called butane. So this is butane. This is pentane. And again, you do not have to memorize the names. At this point, we're going to learn how to name these molecules in chapter 4. I think at this point, the concept itself is more important. So understand the concept. And hexane. Okay, so we have butane, pentane, and hexane. Let me get the numbers from the textbook. Okay, so again, we're talking about boiling points, 0 degrees, 36 degrees, and 69 degrees. Actually, at this point, I think it is also worth mentioning how boiling point is connected to intermolecular forces. I'm not sure if you understand this, but it is sort of very fun when you think about it. You know, let's say think about water boiling. I'm sure everyone's seen water being boiled. You know, so when you heat water and it hits its boiling point, right, the water is converted into water vapor. So my question would be, how is the water in the vapor, you know, the gaseous water, how is that different from the water in your pot? What's the difference between them? Think about it, okay? But what I'm going to tell you is that they're both water molecules, okay? There's water molecule in your pot, there's water molecule in the vapor phase. You do not break anything within the water molecule. And when I'm referring to water molecules, I'm referring to that, okay? So when water in your pot, the liquid water in your pot becomes water vapor, okay, or steam, you do not do anything to this molecule itself. This molecule is intact. What you're doing is you're breaking intermolecular forces. So that means if you have one water molecule and let's say there's another water molecule, we haven't talked about water yet, but there is some intermolecular force between one water molecule and the other water molecule. So this is one water molecule, that's another water molecule. There is some intermolecular force between them. So when we heat it, by providing heat, what we're doing is we are breaking this intermolecular force so that the two water molecules can separate from each other, and then they go into the vapor phase. Okay, that's what's happening here. So whenever we boil something, the heat does not break any of the bonds, the chemical bonds. You're not breaking any of the bonds when you're boiling something. You're merely just destroying all the intermolecular forces and making things boil. Okay, so that brings us back to this London-Dispersion forces, you know, and hopefully makes a connection why we always talk about boiling point when we're talking about intermolecular forces, because the boiling point is a direct manifestation of the strength of the intermolecular force. So if you look at these molecules, they're all carbon chains, but one molecule with 4 carbons in the chain, 5 carbons in the chain, and 6 carbons in the chain. But what you notice is in going from the molecule with 4 carbons in a chain to the molecule with 6 carbons in a chain, that means 2 additional carbons, you've increased the boiling point by about 70 degrees. Okay, that's a lot. Okay, and so why does it happen? What sort of intermolecular forces exist between these molecules? Now, when I say intermolecular forces, we are referring to what sort of an intermolecular force exists between one butane molecule and another butane molecule. We're not talking about what sort of intermolecular force exists between one butane molecule and a pentane molecule, because when we are boiling something, we're boiling a liquid. That liquid is going to be this pentane molecules. It's a bunch of pentane molecules. Okay, so it's a bunch of hexane molecules. That's how you want to think about it. So what is the nature of intermolecular forces between two butane molecules? Because again, as you think about it, I'm going to erase some of this to make room for myself. Okay, as you think about it, if you consider a butane molecule, it's all carbons and hydrogens, so it does not have a dipole moment in it, at least a permanent dipole. There's no permanent dipole in the molecule because the electronegativities of these elements, the difference is less than 0.5. So how could these molecules attract each other? Okay, and so the answer to that lies in basically, how electrons are oriented in space. So what you want to recognize is that this molecule here is a carbon, or is 4 carbons with a bunch of hydrogens on them, right? There are some hydrogens on them. And all of these atoms and bonds, for that matter, they have electrons in them. There are electrons in them. And going back to Gen Chem, realize that electrons are not stationary. They're moving around in space. So you have a probability of finding the electrons in a certain area of space, right? So for this molecule, we're saying that all the electrons that constitute this molecule, or part of this molecule, part of the atoms of this molecule and the bonds, they will be found in this space. So I can, to a very gross approximation, just represent the molecule like a box. Maybe think of it as a box. And what this box has is a bunch of electrons. Okay, not the exact number, but there are a bunch of electrons that are there. And every atom has nucleus and electrons. So the nucleus is positively charged and the electrons are negatively charged. So we have electrons, and additionally we have nucleus again throughout. Okay, so you have these like that. So maybe that's the box. And now the electrons are not stationary. Okay, they have wave and particle nature to them. Or not wave and particle nature to them, but they are not stationary. You have a probability. I don't want to like go too much beyond like what we're supposed to do, but they are basically, there's a probability of finding them around in space. So they're actually moving around. So at some point, while things are moving around, okay, while the electrons are moving around, it is possible that this box becomes a little uneven, okay? So that most of the electrons, they are concentrated on one side, okay? Most of the electrons are concentrated on one side, and there are fewer electrons on the other side. The E represents the electron, the positive charge represents the nucleus. So when this happens, and this is something very transient, okay, something fleeting in time, okay, it might happen for like a fraction, like a very small fraction of a second. We're talking about like nanoseconds, femtoseconds sort of time, okay. So very transiently, electrons all aggregate on one side. And when that happens, since the electrons are negatively charged, this end is going to take up a partial negative charge. And the other end, where electrons are missing, would take up a partial positive charge. So when you started out, this molecule did not have any dipole. Everything was fair, evenly distributed. But during the course of this movement in space, now we've generated a dipole in the molecule. Okay, so it's a fleeting dipole because it is like this at one instant of time, and the very next instant, everything could go back to normal. Okay, so it's a very fleeting situation, very transient situation. But as soon as this happens, okay, as soon as one molecule gets into this mode or gets into this this sort of an arrangement, what it will do is it will influence the electron distribution in a neighboring molecule. So if this is one molecule of butane, and if it becomes a dipole, a fleeting dipole at some point of time, and if there is another butane molecule next to it, nearby it, and this is possible, and this is very much possible, like unlikely in bulk, because when you have a lot of molecules together, okay? So as soon as this becomes a fleeting dipole, it will influence the electron distribution in the next molecule. And so what it would do is, since this end became del positive, it's going to make that end in the other molecule, sorry, this end became del negative, so it will influence the that end in the other molecule to make it a del positive. And the end closer to the del negative will become del negative in the other molecule. So we have a del negative next to it. It influences that electron distribution to make it del positive, and the del positive end thus becomes del negative. Okay, so now one molecule influenced another molecule. So we have one fleeting dipole and we have another fleeting dipole, because this is also going to be very transient, and the next moment this other molecule could become like that. Okay, but as soon as one becomes a fleeting dipole, it's going to influence a neighboring molecule. This neighboring molecule is going to influence another neighboring molecule, and basically that phenomenon goes on. Okay, so it basically ends up influencing like a ton of molecules in that system. And so once you've generated a dipole, what that means is you're going to have some attraction between the two poles. They are going to now interact with each other. Okay, so that's the fleeting dipole interaction. Now it turns out this London dispersion force, LDF, is a function of, okay, not LDF itself. I think I'm going to rephrase it to say that the strength of LDF is a function of surface area. Okay, it is a function of the surface area. That means how much surface is available for contact. So if you have more surface area, is a function of surface area, and in fact I think I'm going to write this. This is directly proportional. Okay, it is directly proportional. So that means if the surface area increases, the strength of the London dispersion force increases. If it is a smaller surface area, the strength of the London dispersion force decreases. Okay, and so now with that background, let's come to these numbers. So what you notice is the difference between these molecules as you add carbon atoms is the surface area increases. So if you have one butane molecule and another butane molecule, they only have this much surface area to form these London dispersion forces. Okay, so this would be our LDF, which is one kind of an intermolecular force. Okay, but when you have two pentane molecules, now more surface area is available. That means you have more London dispersion forces. When you go to hexane, more surface area, and so more LDF. So now if you have stronger or more intermolecular forces, you need more energy to break the force or to separate the molecules. and if you need more energy to separate the molecules, that gets reflected in your boiling point. So when you have a longer molecule, longer chain molecule, the surface area increases, and hence the London dispersion force increases. Okay, so a longer chain implies a higher surface area, which means stronger intermolecular force. In this particular case, it is the London dispersion force, and a stronger intermolecular force would mean a higher boiling point. Okay, so that's how it's connected. And I want to quickly show you another example from the textbook to touch upon another aspect of this. So let's look at another set of molecules where this idea of surface area, okay, that's going to be exemplified. So let's look at pentane, and we have two-methylbutane and so we have 36, 28, 10. Okay, so boiling point is 36, 28 degrees Celsius, and 10 degrees Celsius. Okay. Now, again, I'm not writing down the names, but you can find those in the textbook. The more important point here is, how are these related to each other? Is there a relationship between all of these molecules? Okay, work through the numbers, but what I want you to see is these are all C5H12. Okay, they have the same molecular formula. They all have 5 carbons in them. They have 12 hydrogens in them. But what's different about them? Okay, so they are constitutional isomers because their connectivity or the structure is different. So what is different about them in terms of the structure? So as you notice, going from pentane to this molecule, which is 2-methylbutane, to 2,2-dimethylpropane, that molecule, what you notice is the length of the chain decreases. Okay, the molecules becoming more and more compact or branched. Okay, so this we can say is a linear chain, okay, whereas this is highly branched. And so what happens is, when you have branching, more branching means less surface area. Okay, and if there is less surface area, that means lower intermolecular force, which would imply it's a low boiling point. Okay, so we can again see a manifestation of intermolecular forces and how it's connected to the London dispersion forces in this specific case, how that's connected to the boiling point here. Again, these are all molecules that do not have a permanent dipole in them. Okay, so the interaction between two molecules would be the fleeting dipole kind. Okay, so we've discussed the dipole-dipole interaction, and then we talked about London dispersion forces, which are the fleeting dipole interactions. Okay, now the fleeting dipole interaction is weaker than a dipole-dipole interaction. We will discuss about hydrogen bonding in the next video, and after that we're going to summarize all 3 intermolecular forces.